That's recording. I'll stop it. Okay, so I want to talk about work. Work is this is really a physics topic, but there's such a beautiful application of integrals that we bring it into calculus. So the basic idea of work is just force times distance. How much force it takes to move something and how far you're going to move it. So if I want to pick up something like this really heavy eraser, so the work it takes to pick up this eraser has to do with how heavy it is, because that's going to determine the force, and how far I'm going to lift it. So if I only lift a little bit, it doesn't take much work, right? But if I lift it way up here, that takes more work, because I'm applying this force for a longer time. That makes sense? So the work done is calculated by how much force it takes to move the object, and then how far you're going to move it. See, that's what the FD stands for. And if the force is constant and the distance is the same, then it's pretty easy. There's no calculus involved. You know, like if you wanted to pick up a 50-pound weight and you wanted to lift it, 3 feet. Okay, what is the work done? Well, that's just 50 pounds times 3 feet, which is 150 pound-feet, which actually is a unit of measure. You can convert that into other things, but so that's really straightforward, right? There's no problem there. We just multiply work times, force times distance. The problem comes in if one of those things is changing. So sometimes when I'm lifting something, maybe it's getting lighter, or maybe it's getting heavier, or whatever. So the force is changing as I'm lifting it. Or, like for example, if I have if I'm picking up something that's attached to a rope, so I'm pulling up, say, a bucket of water out of a well. Well, I'm picking up the weight of the water in the bucket, but I'm also picking up the weight of the rope, aren't I? Does that make sense? So when I first start picking it up, it's really heavy because it's got the full weight of the rope and the weight of the bucket. But as I, start pulling it up, and the weights and the rope's falling on the ground and curling up, well, that weight of the rope is being taken off of my lifting, right? So it doesn't take as much force anymore. And the further I go, the lighter it gets because I'm having less and less rope. Does that make sense? Or if it's chain, it's even worse because the chain is heavier, right? Or if it's in a well, it's worse because the rope is wet, so it's extra heavy. So that's the idea. So when we have something like that, then we have to use calculus because the integral can get at a changing force or a changing distance. Okay? Everyone got it? So the idea is we have to figure out what it is we're lifting, break it into little slices, and make an integral out of it. Okay, so number 1 says, a tank contains 288 cubic feet of water. If the density of water is 62.4 pounds per square foot, or cubic foot, how much work is needed to pump all the water out of a spigot? That reminds me of a funny family story, but I don't have time for it now. Okay, talk about it. How would your integral change if that's a question after we're done. So we got this big square block of water, and we're going to be lifting it out. Now, here's the problem. The force doesn't change, right? What determines the force in this problem? The density of the water. So this says that each cubic foot of water weighs 62.4 pounds. So that's the force it takes to move it, right? So that's the same no matter what. So, but the problem is that we're not going to move the whole block of water at once, right? We're going to be pumping, so much. I don't know how it works, but there's a little pump and a little, pipe or something, and it's going to be squirting out the top, right? So it's not like it's a frozen block of ice where we're just going to grab it and pick it up. Then it would be straightforward, right? We're going to pump it up in increments. So the way we do it is we break it into little slices. Because everything on the bottom of the tank, see if this makes sense. Everything on the bottom of the tank is going to be pumped the same distance. You buy that? But the stuff in the middle of the tank, like this little slice here, Doesn't have to be pumped as far, does it? You with me? So if you get to the top, well, it's already on the top. All we have to do is just kick it out. So there's hardly any work there because it's not, the force isn't going to be applied very far. So what we're going to do is we're going to break this into little slices, and we're going to pump one slice at a time, right? We're not going to really pump one slice at a time. The integral is going to do that for us, okay? So we're going to break this into a little, and so the slices are this little thing I've drawn here. I'm going to make it a little bit bigger, and I'm going to erase it and redraw it because I did it real roughly. So it looks something like that. Put a little bit of thickness to it. So we're pumping a rectangle of water, okay? Now, of course, it's not going to stay in that shape, but all we're worried about is that whole rectangle of water is going to be pumped roughly the same distance. Do you buy that? Okay, so we're going to take this bit of water here and we're going to pump it. Okay, so what is we need to figure out the force and the distance that slice of water that's happening in that slice of water. What's that? Well, it's a 62.4 pounds per cubic foot, right? So that means we need to take 62.4 and multiply it by the volume of the water, right? You buy that? Because we need to know how much cubic foot it is, right? It's not just 62.4 period. It's 62.4 per cubic foot. So I need to figure out how many cubic foots on feet. What is? I'm trying to figure out how many cubic feet of water it is and then multiply that by 62.4, right? So it's definitely going to involve, force is definitely going to involve 62.4 times something, right? What is it times? It's times the volume of that little slice of water, right? What is the volume of that slice of water?
280 cubic feet? No, that's slice of water.
Just the slice of water. Just that little slice I drew, for example. Exactly. Area times dy. And the area would be 12 times 4, right? Isn't that the length and width of that little slice? So that's going to be, what, 48 times, and we'll put in a dy because that'll be that little thickness. Okay, everyone see why John said dy? Well, technically it's not dy yet because we haven't really determined our axis, but that's probably what we do instead of the axis is going up, right? I mean the y-axis up and the x-axis down. Okay? So that's the force. Everyone with me? Okay, now we got to figure out the distance. Now here's the problem, right? Because we said each slice of water is going to be pumped a different distance. So if we set, let's see. Do we care about the x? We don't really care. So let's set our axis right here. There's our y-axis. There's our x-axis. So the only reason we need x-axis is so we know where 0 is, right? So as y grows, what happens to the distance the slice is being pumped? It gets smaller, doesn't it? So the top y is 8, so that means my distance is going to be 8 minus y. So see, this makes sense. If I'm sitting right here, right, how far am I going to pump it? If this, in other words, if this is y, this distance is y, I'm going to pump it 8 minus y. That make sense? I drew too many lines in there, didn't I? It's hard to see. Let's go over here and put it over here so you can see it better. That's my x-axis, that's my y-axis. So we're saying right here is y, because that's that uniform little slice that we're moving up and down. So that's y. This distance up here is 8, like it says. So the distance that this slice of water is going to be pumped is right there. You see that? The red slice is the distance that slice, the red line is the distance that slice is going to be pumped. And what we're saying is that distance is going to be 8 minus y for any slice. Right? So if we move the slice up to here, oops, let's go back to green. If we move the slice up to here, okay, here's the new slice that I should be able to, it should be working for it too. So now my new y, and my new y is right there. Notice the distance that I'm pumping, it got a lot smaller, didn't it? And so once again, the distance that I'm actually pumping is, come on, dude. Yeah. The distance I'm actually pumping is right there. See how it's much shorter? But it's still 8 minus y. Okay? So, my integral, ready for the integral, everyone? Yeah, give it to us, give it to us. The integral is going to be force, which is, stop that. The integral is going to be force, which is 62.4 times 48 dy, and we're going to multiply that by the distance, which is, 8 minus y. Of course, that's not a really proper way to write an integral, because that dy should be mixed in with it. So what I'm going to do is take the 62.4 times 48 and put it outside, and then we'll just have an 8 minus y dy right there. Now, we only have one thing left. What are the limits of integration? 0 to 8. Because that's where the water is. Yes? So the density of water is, that's a good question. So the density of water, remember, is, I should have included units here to help you see it better. The density of water is 62.4 pounds per cubic foot, right? Right. So it leaves you just pounds. Pounds is a measure of force. Yeah. It's both, yeah. Weight is force. So basically, it's one way to measure force is that you have to, I mean, there's other units of force, but pounds is one of them. Yeah.
You're thinking of mass. Mass is like the actual substance or something, but that's not gravity.
Right. Yeah. Oh, thank you for translating that. Yeah. Okay. Any other questions? Yeah.
What's the y?
What's the y? Well, remember I drew in I'm bringing the xy axis to it, right? So I just put the y as right. Let me get a different color here. Why is that giving me so much trouble? The y is right here. The y-axis is right there. So the bottom is 0. You know, where the bottom of the tank is 0, and the top of the tank is y equals 8. Okay. So remember, in these word problems, we're bringing the variables to it, right? So you could just throw out the x-y-axis and just say, instead of x or y, I'm going to use h as my variable. What's h? It's the height of water. It's the height of the slice of water that I'm talking about. You know, you can define the variable any way you want to. I think it's safest, because we're so used to X and Y axis, to just put an X, Y axis somewhere on the problem and then just use that. But sometimes it's easier to do something else. If you want to define the variable, you can define the variable however you want to. Just got to be clear on how you're defining the variable. If that makes sense. Okay? Okay, any other questions about that? Before I try another one. Oh yeah, so the second question was, how would your integral change if the tank is on one of its other sides? So we'll just talk about this for a minute. So instead of laying the way it is, what if it's standing upright? How would that change the problem?
Your Y would change 12.
Your Y would be from 0 to 12 now, wouldn't it?
The distance would be 12 minus Y.
The distance would be 12 minus Y. Good. That's a good question. Someone argue back with John if they want to. John says that's going to take a lot more work to put it upright. Do you all agree with that? Yeah. So you're pumping it a lot further. We all agree with that. Yeah? But the volume you're pumping is smaller But the truth is that you're going to pump the same amount of volume when you're all done, right? I mean, it's just cut up in smaller slices. So I think John's correct, but I want to not just go, oh yeah, John said it's true. I want us to think about it, and see if it really makes sense. But that's the immediate thought as we turn it upright and like, okay, now we're pumping 12 feet. We're not pumping everything 12 feet, right? We're only pumping the bottom layer 12 feet. And the bottom layer is smaller than the layer that I pump 8 feet, right? So it might be interesting to calculate and see if we all agree. But that's my initial thought, is because you're pumping everything eventually, and you don't really let's see, the part that's below 8 feet, that's going to be a significant part of the water. But anyway, that's something you can play around with. It says, and that the final question is, which thing we're just discussing is which position would produce the greatest amount of work. My suspicions are along the lines with John, but I'm happy for someone to test it out and come back and say we were wrong. Okay, number 2. A tank is full of water. It's a different type of tank now. This makes it a little bit harder because it's not a nice rectangle. Rectangles are nice. How much work is needed to pump all the water out of the tank to a point 3 feet above the tank? And then the second question is, how would your integral change if the tank is on its side? And the answer is really, really difficult, so don't even try it. But just kidding, we'll look at it. But it is a lot harder if it's on its side. Okay, a tank is full of water. How much water is needed to pump all the water out of the tank to a point 3 feet above the tank? Well, this is similar to stuff we've been already doing, right? Can you see the slices that because we're going to use the same method. We're going to slice this big tank of water into little slices. What would the slices look like? Little mini cylinder or disc. Yeah, this is like the disc method again, isn't it? So I'm going to draw one of those little discs. So in other words, there's a spigot coming out like this. And I'm not just pumping it out to the top and dribbling over. I'm pumping it up beyond the top and out further. So it's just extending the distance, right? So in the end, the tank is 5 feet, but I have to pump it another, what did I say, 8? 3. I have to pump another 3. Yeah, so 8 total, right? So the total distance from the bottom is going to be 8 feet, right? Yeah. But notice this, well, we'll get into this. It changes the distance, but it doesn't change the limits. So we'll make sure we understand that. Okay, so we got force times distance, and I always start with this so I can figure out what goes into what. So you can put little parentheses there for your force and for your distance, right? What's the force going to be? It's water again, so that's 62.4. And that's multiplied by what, do you think? The area times dy, right? And the area would be 36 pi. Okay, everyone see where those are coming from? The 36 pi is just the area of the circle, yeah. We're doing 62.4 times the volume of that slice. That's where the 36 pi dy comes in.
Yeah, I was saying the volume would be the number of water.
Right, it's full of water, but what we're gonna do is not look at the whole tank at once. We're just looking at one little slice at a time. Okay? So, and of course that slice is generic. That's where the dy comes in, right? And that's where the y is going to come in. Yeah.
And what is the 36?
What's?
What is the 36?
The 36?
Yeah.
That's the area of that circle, because notice the diameter is 12. Make sure the radius would be 6. So that's pi r squared. Right? The area of the circle is pi r squared. And the radius is 6. So that would be 36 pi. And then notice the height of the cylinder, if you will. That's where the dy is coming from. So there's 6. So that's where the 36 pi dy comes from. Okay? Any other questions before I move on? Yeah.
Diameter is 12.
Yeah, I know it's miles square.
So the diameter is 12. You see the 12 at the top? Yeah, okay. It was kind of covered up by the spigot. Okay, now, what's the distance being pumped? If we set a little y-axis here, the y-axis is sitting on the spigot, and the bottom is right here. We're calling that 0, ground 0. So it's going to be what? 8 minus y. Because as I get further up the tank of water, the distance I have to pump it gets shorter, right? So my basically the depth of the disc that I'm looking at is subtracted from 8 is going to give me the distance I have to pump it. Okay? Okay, so let's organize this a little bit. I'm going to put the 62.4 times 36 pi times the integral of 8 minus y dy. Now, the limits of integration. 0 to 5. Good. Not 0 to 8 because there's no water in that spigot. We're just taking, whoops, why did I put 2 zeros? 0 to 5. We're just like in the volume of revolution things, the limits are determined by the region that I'm dealing with. In these, the limits are determined by the space where the water is. Right? In fact, what if I would have said this tank is only half full instead of completely full? Yeah, and everything else would be the same, wouldn't it? It doesn't change anything else. If I said the tank is only half full, this would go from 0 to 2.5 instead of 5. So you see how much water is in the tank determines the distance or the limits of integration. What if I said I only wanted to pump the top half of the water out? So let's say I have like a floating pump. It just starts pumping and it just pump until it gets down to half and it stops.
2.5 to 5.
2.5 to 5. Yeah. Or we could change the whole system and put 0 at halfway. And there's a couple different ways we can do it, but the way we have it set it up, we can leave everything the same and we just go from 2.5 to 5. Does that make sense? We're going from halfway to the top. Okay. Now, let's look at this, the tough booger for a second here. How would your integral change if the tank is on its side? We're still pumping to the top, though. Yeah, oh shoot is right. Looks like a submarine. We're still pumping to the top. So now your slices, what do your slices look like?
Rectangles.
They're rectangles. But they're ever-changing rectangles, right? There's these teeny little rectangles at the bottom, and they grow and grow and grow to get biggest they're going to get halfway, and then they start shrinking again, don't they? See how that makes this problem a whole lot more difficult? So the moral of the story is, if you bury a tank of water, bury it upright, don't bury it sideways. Because it'll be really hard to calculate how much work it takes to pump it out.
Or just don't worry about
I beg your pardon. What?
I'm saying the whole thing is a lot easier to dig the hole the other way, and I'm just going to ignore the work.
Not if you have a... yeah. Anyway, so what does it look like? It looks... Hey, hold still. We're going to have this little rectangle here, right? This is going to go like that, and like that, and like that. Thickness. So in this case, we have to consider the x and the y and stuff. So what I would do is put a little y-axis right there in the middle. And I would actually put my x-axis in the middle, right in the smack dab middle of the tank, so that when you hit the middle of the tank, you're at y equals 0. That's what I would do. Now, once we've done that, how does that help us?
Figure out that formula for that.
So how long is the rectangle? Is it really? Oh, it is. That was longer. Okay. So the rectangle that we're dealing with right now is 5 feet by something, and the something is the problem. Right? The 5 feet doesn't change no matter where I'm at. It just gets skinnier. Or it goes from skinny to wide back to skinny, right? So so what we want to do is somehow relate our y to our x. You buy that? Let's look at the end of the tank for a minute. Here's my y. Here's my x. And here is my radius. Okay. So what is the radius of this thing? 6. So we know this distance right here is 6, right? So now what is this distance right here? This distance right here. That's a y value, isn't it? Now this is why I put 0 at the middle there, because this right here, this distance that I just drew in is the negative. So let me say, for example, if this is, say, what's the total y there? 12, isn't it? Yeah. So let's say this is like -5 here. Okay? You see how that would be a y value, right? So if that was -5 and this is 6, then I could calculate that x value right there, couldn't I? That make sense? What's that? You need another color, don't you? Sorry, John. You want to know what that distance is, right? Because that's going to determine the width of the rectangle, right? So you can see if that was -5, this would be 36 minus 25 square rooted, wouldn't it? See that? Of course, it's not -5, it's -y, right? I mean, it's y, but it's going to be a negative number. So we don't care because it's going to be squared, right? So this red distance is going to be 36 minus y squared, square rooted. And that red distance happens to be that distance right there, right? So if I'm trying to find the area of this rectangle, it's going to be 2 times the square root of 36 minus y squared. Notice that works whether I'm above the middle or below the middle, right? Because I'm either squaring a positive y or squaring a negative y, and either way it works. So now my integral is going to be 62.4 times 10 times the square root of 36 minus y squared, and all that's just the force. The distance is going to be
12. 19. 15 minus 1.
where are you guys getting 15?
You have to add the extra 3.
Oh, the extra 3, that's right, yeah. 15 minus y. Does that work? Just accept it because Connor said it. Does that work?
Balance for the
Can't be 0 as well because
negative 6 to 6.
it has to be negative 6 to 6, doesn't it? Right? Because that's where I put the middle thing. So that 15 isn't going to work, is it?
It has to be negative 6 to. Or no, sorry.
We can't change the limits because that's the way we determined it, right? Yeah, 9 minus y. There we go. So notice that 9 minus 0, that would be the right distance, wouldn't it? Right? When y is 0, that would be, we'd be pumping at 9 feet, which is what we want. When y is negative 1, 9 minus the negative 1 would be 10, wouldn't it? So it still works. Yeah. Yeah, we had to adjust that top distance based on where we put our x-axis. Yeah.
Couldn't you do like the cross section with semicircles, except don't divide in half?
Well, if you're taking them from the top and you get the cross section. Oh, are you talking about cross sections going up?
Well, I mean, it's all semicircles down the entire line of a rectangle.
Yeah, the problem with the top of the semicircle is being pumped 3 feet, but this one's being pumped more. So you have to divide it up into sections that are being pumped the same distance.
Okay.
That's why we had to do a rectangle. You're right, there's a lot of different ways we can pump that. We can slice it, just that we have to cut it into slices that are all going, everything in that slice is going the same distance. So we really have to slice it perpendicular to the way that I'm pumping it. So when I'm pumping it this way, I have to slice it this way, right? Okay. Here's the next layer of difficulty. Well, the one we just did was about as difficult as they get, but we'll come back a scale, but we'll scale up the one before it. So, a conical tank filled with kerosene is buried 4 feet underground. The density of kerosene is 51.2 pounds per cubic foot. The kerosene is pumped out until the level drops 5 feet. How much work is needed? So that's kind of like I said before, we're just pumping the top 5 feet of the kerosene. Okay? How much work is needed to pump this kerosene to the surface? Okay? What do our slices look like?
Circles.
They're going to be circles with circles with height, which is disc, yes. So we're going to have a little disc here. Now, once again, why this is a little bit more difficult is because the discs they're growing as we get up, right? Or shrinking as we go down. They're getting smaller as we go down. So we have to come up with something like that. So we're going to start off with the force. What's the force? The force is 51.2 times the volume of each disc, right? The volume of the disc is pi r squared times dy or d depth or something like that, right? So 51.2. Now, pi stays pi. Dy is going to stay dy. What is it that I want to square?
6 plus x.
1/3 Y.
Y.
Got all kinds of good ideas here. So remember with cones, the radius and depth or height are in a certain ratio, right? So we can see right now that the radius to height ratio is 6 to 8. In other words, 3 to 4, right? So we could say that the radius is 3/4 the height, which is what we want because the height is what we're going to measure, right? The height is the thing that I'm going to be pumping it up. So we know that R is equal to 3/4 H. Y'all buy that? And so then I think it makes sense to zero out right down there and then pump up to there.
Would you change our H into no?
We could.
Would it be easier?
Easy. I think it's probably easier to understand to zero out at the bottom because you can do that all the time and then just adjust your limits. But definitely, if it makes sense to you, just zero out there. You can do that. You just have to define your variable. That's the problem with. It's easier to define the variable. Just say that my H is my Y. Or the depth of the water is the Y. That's a pretty easy way to define it. If you do it the other way, you say the depth of my water is my variable is the depth above 5 feet. You know what I'm saying? It's just but if you can wrap your mind around it, that's great. Okay? Okay, so what do? We're going to call that Y now, right? Instead of H, because we got a little XY coordinate system here. So then we're just going to put 3/4 Y right in there. Or 3Y over 4. No, here's my ratio, right? So when I solve that, I just multiply both sides by H and I get R equals 3/4 H. Right?
If you're doing it on like the XY plane, Y equals 3/4x. Up 3.
No.
Oh no.
No, other way around.
Four,
Yeah.
three,
Yep. So now we got to figure out the distance pumped. So my integral is going to be 51.2 on the outside, 51.2 pi on the outside, and I'll have 9y squared over 16 because I just squared everything. So I can move all that out too if I wanted to. Now I need my distance in here, and then I'll put the dy at the end. Okay? And we might as well do the limits over here. Where would the limits be? From 0 to?
5 to.
Oh, right, because they're starting at 5, yeah.
9.
5 to?
8. Yeah.
5 to 8. There we go.
No. Dropping 5 feet is only 3.
It means drop 5 feet down. That's a long drop.
Oh, so it'd be 3 to 8.
What about the extra 4 feet that you have to go to travel?
Well, remember, we don't have to worry about that in the limits. That's going to be worked out in the distance I'm pumping it, right? We just want to make sure the limits just tell us where the water is that's being moved. So the water that's being moved is from 3 feet up to 8 feet. Okay? Okay, everyone see where we got the 3? Because I've misread that. Where the kerosene is being pumped out until the level drops 5 feet. I think I had in my mind drop to 5 feet, but it's dropping 5 feet. So if you drop 5 feet from 8 feet, you're down to 3 feet. So 3 feet, when you're done pumping, there's going to be 3 feet of water left in the bottom of the tank. So that's why we're pumping from 3 to 8, because we want to pump. The water goes up the top of the tank. Now, what's the distance? Yeah, but you're adding it to 8, aren't you? So think about this, that the 8 foot At the 8 feet level, at the top of the tank, how far am I going to pump it? 4 feet. Good. So we would want that to be 12 minus 8, right? To get 4 feet. How about the 3 foot level? How far are you pumping it?
So it'd be 12 minus y.
Yeah, 12 minus y.
Because your y is inserted.
If you're having trouble with that, just check the two limits. Think, I know that when it's 8 feet, it's got to be pumped 4 feet, and I know when it's 3 feet, it's got to be pumped 9 feet, right? So then just come up with the right thing that produces that. But again, in general, it's usually just the height that you're pumping it to minus the depth of the water, because that's as the water drops, the distance you're pumping gets farther. Thank you. Okay, so number 4 is a good one to practice that on, because it has the tank is filled with water. It gives you three different scenarios where it's kind of the same idea. So I'm going to hop to the number 5. I'm going to plug this in so I don't run out of batteries. There's 3 right there. Okay, a worker on a roof 50 feet above the ground. Let's draw a picture. That's 50 feet. Needs to lift a 300-pound bucket. Ooh, that guy's strong. Of cement from the ground to a point 20 feet above the ground. By pulling on a rope weighing 4 pounds per foot. How much work is required? So this is similar to the water. Remember we talked about density. The density of the water was 62.4 per cubic foot. So now we have rope that's 4 pounds per foot, right? So that means every foot of rope is going to add an extra 4 pounds. So what we have here is this rope that's coming up top, and he's pulling on it. So when he begins, how much weight is he lifting? Now you were going to pretend that the bucket is negligible in height, so it's like flat on the ground. So it's a really dense bucket. It's really. So how much weight? Can you calculate how much weight he has to lift for the first pull? How much weight is it? This guy is strong. So 50 times 4 would be the rope, right? Plus the 300-pound bucket. That a total of 500 pounds. So his first pull. This is Robocop. First pull is 500 pounds. No problem. Okay. All right. But then his next pull, let's say he does a full foot. Now his next pull is not going to be 500 pounds anymore, is it? 496. Oh, that's much lighter. Yeah. What's that?
I don't understand.
Well, it's 300 pounds for the bucket. For the bucket, plus 50 times 4 for the rope. 50 feet of rope, right? Because he's standing on the top of the building 50 feet tall. Yeah, because you got to lift the weight of the rope plus the weight of the bucket. Now, if he had an invisible force field or a rope, like maybe he has an elven rope that doesn't have any weight at all, if he was lifting just the bucket, do we need calculus? We don't, because the weight of the bucket is not changing, right? So we could just throw the bucket out for a minute. Actually, we'll deal with it first, and then we don't have to worry about it. So what's the actual work done for the bucket? Work done for the bucket. He's got to lift it 20 feet, 6,000 pound feet. Now I can forget about the bucket. Isn't that nice? Didn't need no calculus. And what am I going to do with that 6,000 pound-feet when I'm done calculating the work done on the rope? I'm going to add it, right? Because it's just extra work that he did. You know, it's like he lifted the rope up and then later he lifted the bucket up with an invisible force field. Okay, so that's done. Work done on the bucket's done. Now we're just going to look at the rope. Okay? So now this is kind of like water. We're going to take a little slice of rope and we're going to calculate how far it moves. So the bottom rope is going to move a lot further than the top rope, right? Does that make sense? So the force, so we still need force and we need distance, right? The force is going to be 4 pounds per foot times the length of the little segment we're making, but we're breaking it into teeny little segments, so that's going to be dy, isn't it? So the force is 4 pounds per foot times the length of the little segment, which that's my dy. Okay? That makes sense? No, because we know the way the weight is given to us is it's just 4 pounds per foot. There's obviously volume to that rope, really, but it's just saying someone's weighed it in the past and said, well, every foot weighs about 4 pounds, you know. So we're just calculating it. It's really and here it's a linear measurement, but you're right, it's actually a volume but they've told us to it in, you know, it's like they took a section of rope and said, this weighs 4 pounds. So I'm like, all right, I buy it, you know. So I don't need volume. I don't need to break it into little, okay? Each foot of rope weighs 4 pounds. Yes? Right, so I'm taking this little section of rope and saying, okay, how much does this section of rope weigh? Or how much work does it take to move this section of rope? And this section of rope is, you know, we could think of it as a foot of rope. It'll take me 4 pounds to move this foot of rope, right? But then I'm going to cut it in even smaller, but it's still 4 pounds per foot. So I'm measuring dy in feet, and I'm multiplying 4 pounds per foot times dy, which is feet, and that gives me the poundage of that little segment. Okay? So in other words, we're saying, how much does this little segment here weigh? That little bit right there. Well, the length of that bit is dy, right? What's the weight of that bit? It's 4 times dy, 4 times the length. Okay? That's what's confusing about a lot of these. There's two lengths. There's the length that you're moving it, and there's the length involved in either the height of the disc or the length of the rope, right? Okay. Now, distance. How far is that length of rope going to move? 50 minus y. If we're thinking of a 0 being down here, right? We're calling this 0 and we're calling the top 50, right? So it's going to move 50 minus y. When I'm at the bottom, it's got to move wait a minute. Hold on a second. We're only moving at 20 feet above the ground, aren't we? Whoops! Okay, back up. We're not hauling it up 20 feet. We're just hauling it up 20 feet, right? So the rope, yeah, there's two different ways to look at this. We can go with 50. Yeah, we just have to do the limits different, right? You're right. So doing it this way, what are my limits of integration? Yeah. 30 to 50. So think about this section of rope right here. How far is it going to move? Okay, yeah, the top foot is only going to move a foot, right? So at 49, how far is the section rope at 49 feet going to move? 1 foot. So we went 50 minus 49, right? How about at 48? How far is that one going to move? 2 feet, yeah. So that's what we want, right? How far is the is this little section down here going to move? The section right above the bucket. It's only moving 20 feet, right? But the problem is that it's not, it's still going to be hanging there when we're done, right? It's not going to disappear, right? So when we did this 6,000 feet, right? There's actually more there than we should have added more weight to it. So this section that's changing is just this top section of rope here. Are you with me?
Yeah, so you have to add the extra stuff that
This is a good question to illustrate the idea of you got to figure out what it is that's changing and why we need to use integration. So let me ask this again. We'll back up to the very beginning again and ask it. Do we need integration for this section of rope? Okay, hold on. Let everyone think for a second, Connor. Do we need integration for that section of rope? It's not, because we're only going from 30 to 50. See, we're only looking at that top section of rope, just the top 20 feet.
If we went from 0 to 20, though, would that give us that extra 30?
If we went from 0 to 30, if we went from 0 to 20, then we're ignoring the other part. So no matter what so remember the limits. I'm going to pause this here until we work this out. Is that right there? So my final integral is that plus the 6,000 feet or pound feet from the bucket plus the 120 pound feet from the rope. So the 30 to 50 will take care of that top section of rope that's kind of slowly disappearing. The 6,000 will take care of the bucket, and the 120 pound feet will take care of the rope, this section of rope right here, that just hangs there the whole time. And it'll still be hanging there when I'm done. Okay? Okay, if I was you, which I know I'm not, but if I was you, I would go home and do that take-home quiz and get it done tonight. That's what I would do. The best you can, come with some questions tomorrow. Do it Wednesday. If you put it off and do it tomorrow night, you won't have you'll have less time to ask questions about it. But I seriously think if you sit down, this is what I would do. I would go home and spend an hour on this. And then just set it aside. If it takes more time than that, then you need to come see me.